So for this case study, we're going to look at a piece of equipment called a mechanical ventilation heat recovery, MVHR, which is a key part of one of the main strategies for ventilation in zero carbon buildings. Before we get into that, I want to set the context a little bit and look at the options. So there are two main options for ventilation strategies when it looks at zero carbon buildings. One is called natural ventilation, and the other is called what I call the seal box method with mechanical ventilation heat recovery. So natural ventilation is the type of technology we use in our block, and it usually has a very active facade, so windows on the edges of the building that are automated open and close, or louvers which automate open and close, and then some way of drawing air up through your building. It's using two natural forces, one of wind pressure or at the sides of the building, but also of the hot air rising up through the building. And in fact, in the worst case scenario, in the middle of the summer, when you kind of have to assume there's no wind, so you're actually even designing for just the buoyancy factor of pulling enough air through this building just by the fact that hot air is rising in that worst case scenario. So if you had a building like our block and you had a studio and maybe a classroom and a computer room, each of these are going to have different levels of air change, different requirements of ventilation, and so this system is going to need to draw enough air through this building. How that works is it starts with a draft up at the top, so you can see these chimneys here. If you extend the length of those chimneys up or put them up into the airframe, you're going to get a draw up through that building. The rate of that draw will determine the amount of pressure you have to pull through the building as well. So there's techniques we have of increasing that draw too. Sometimes you can use a cowl which moves around with the wind, or you can put maybe a solar connector in there and a window which superheats the air and causes the wind to move even quicker. And then when you have that draw, sufficient draw, you can then pull air through these rooms and into the building by automating a window, opening a window, or like we have in our block, behind the radiators there's a louver, a very quiet louver that opens up and closes automatically, and that will determine then with the sensors in the room, measuring CO2 levels for freshness, measuring temperature for comfort, and determining what level of the windows need to be open, and that draw then is released. We have 7 big chimneys in our block that are doing just one half of the building to the north, and then the spaces to the south are being done using the atrium up here through the middle. Again, most are just done by an atrium, and this top hat section is the section that actually causes that draw in the first place, which again pulls that ventilation level through. It may be that the calculations show this is quite a complex design. Natural ventilation calculations may show you at the worst time of year you may need a little booster air, so you may put in a fan or two just to cater for that worst case scenario. Especially if the 3 examples I gave of a studio space or an office, a computer room, and a classroom, because of the densities in there, your computer room with lots of students, that might actually be a scenario that you'll say, I'll put a little booster fan on that just for those worst case summer days where with the computer heat and the people heat, the load is just not sufficient to be met by the actual draw of the building. So that's the ventilation strategy. If you're an architect, the main shape is from your facade about 8 meters in, and then the air wants to turn and go up. So that basic shape is the determining factor of your natural ventilated building. Quite a few times I get architects coming to me, student architects, and they have a fully designed building. They go, now I want to make it naturally ventilated. And I'm going, I'm sorry, you have to decide that at the beginning because it has such a big instrumental shape influence on the shape of your building. From your facade, about 8 meters of horizontal movement before that air wants to turn and go up. That's about the main shape. There are techniques for doing that, for extending that. So there's one where you put a solar chimney on the side of the building, gets full exposure all the way down through its length of solar energy, and then the air that gets pulled up there is very rapid. And so yes, you could draw air longer distances than 8 meters, but that's very experimental and very rare. Much more common is actually just to have an atrium in the middle and be drawing it through the atrium, and then if you get an issue, you might have to extend the length of these up into the air if you need a situation where you have to draw particularly more air through one of these buildings. So that's natural ventilation, very active facade, drawing air in from the outside, but very low energy because we've reduced the need for a fan moving the air around most of the time. There is a major drawback in that we are assuming the air outside here is clean enough. The air quality is clean enough. They say that only about 30% of London could even consider natural ventilation because of air quality issues. And so we have to look around our building and see is there going to be pollution from cars or noise or smell from something nearby whereby natural ventilation is not a good strategy. And in that case, we go to the other strategy, the sealed box strategy. You walk around London, you don't see openable windows in most buildings. They're all sealed up because they're using this strategy. And this one, it's much more invasive of the structure. You have to make your structure as airtight as possible. So you want to get this structure right down to be airtight in order to fit this technology called mechanical ventilation heat recovery. And it's donated by the supply air, putting fresh air into the building. That fresh air then gets moved across the building into the staler spaces where there might be odors or moisture. That gets picked up and that gets taken back. There's heat recovery. So without the air mixing, the heat from the exhaust air gets passed into the fresh air. And so you get warm, fresh air coming in, and you get cooler, stale air exhausting out. Again, those air streams don't mix. They come close to each other. So we keep the heat and we lose the staleness. That's the key magic bit happening there in an MVHR. So that's the technology that's needed for that other sealed box method. The passive house system uses the sealed box method. So despite sometimes passive and active being donated for one having a fan and one don't, actually the passive house uses mechanical ventilation heat recovery and the sealed box method. It does not use natural ventilation. Sometimes people say, why not have something called mixed mode? Have both systems. And sometimes during the day it does mechanical, and then the mechanical turns off and the natural takes over. That could work in theory, but it's usually an economic barrier because you're now paying for two systems instead of one. So it's usually a cost issue rather than a technical issue becomes the scenario there in terms of making those things feasible. A lot of buildings where they're not zero carbon buildings, they're quite leaky buildings, typically do work in mixed mode operation. They have a mechanical system and at 6 o'clock in the evening, enough people have gone home maybe and it turns off and they're still okay with just localized air ventilation. So, but when we talk about high performance zero carbon buildings, it's harder to justify the economic cost of doing both high level nat vent and high level sealed box system. So exploring this technology a bit more, if passive house uses the technology, it's worth knowing a little bit more about that. I talked about the air, how it works. Its donating features are a number of supply air ductworks. If you're used to commercial environment, there's an analogy with what we would call an air handling system. So instead of being the size of a small fridge, it's the size of a caravan, but it's basically doing the same thing. There's a set of ductwork going. This is the walkie-talkie building in London, stripped of everything except its mechanical ventilation systems. But it's the same thing up here. You have big pieces of kit, which are multiple numbers of this. They're taking air from outside, they're filtering it. You get injection of heating and cooling in here in these ones, which is the reason why it's not passive house. And then you get that fresh air, conditioned air being pumped down into every floor and supplied into every floor. Normally in a grill spread out around the room so that you don't get chills. It's normally gently introduced to the room at the ceiling level, or sometimes underneath. Gently in multiple spaces so that you don't get any localized drafts. So you notice the shape of the grill is designed to introduce the air comfortably into the space. Sometimes if we want to rapidly increase that air rate, we might use something like a canvas bag system that we can maybe put more air in and disperse it through the space more rapidly if we want to get a higher air change rate through wanting to cool by ventilation rather than artificial cooling. There's a technique for doing that as well. Then the return air comes back on a separate set of ductwork. Again, that's very common in commercial buildings like this, a complete second set of ductwork coming back up to the air handler units. So you can see there, one would be a supply going out, the other would be the return coming back. You do some form of heat recovery then. In commercial systems, there's three main types of heat recovery. There's plate heat exchangers, which is what is on a domestic level MVHR. They come close to each other through plates, metal plates. They don't mix the exhaust air and the fresh air. The heat goes through the metal, and that's how the heat exchange happens. In commercial scenarios, you also get an option called a thermal wheel. A thermal wheel is something that slowly moves from one airstream into the other. It's made of a heavy thermal mass, and it picks up heat in your exhaust space. And then as it turns into the fresh air, it drops that heat back again into the fresh air. These two systems are about equally as efficient as one another at recovering that heat. A little problem with the thermal wheel. They've been banned in hospitals in the UK for a while now because of a potential issue with contaminants, colds and flus getting onto the wheel and going into the fresh air. And I imagine with the current remit, they're becoming even less popular. Although there are reputed to be techniques for making sure that doesn't work either, which are emerging. I think it'll probably become a less popular option, the thermal wheel over the plate heat exchanger. If then you just cannot coordinate your return air to come too close to the exhaust air to use one of those two, you could effectively use a heat pump, or called a runaround coil. You stick one end in the exhaust air, and you stick the other end, and you do an air source heat pump, a runaround coil in that space, and it tends to be slightly less efficient than the other two. But the good thing about a runaround coil with a heat pump is you're not limited in temperature. You can actually keep pumping heat out of a colder space into a hotter space using the vapor compression cycle, which I explained in the video on heat pumps. The effectiveness really depends on the air tightness of the structure. So we had a good example here a few years ago. We did an air pressure testing of 3 houses in Bristol that had the MVHR technology. One was a DIY. Someone bought the MVHR, brought it back to his house, stuck it in the attic, put it on the tubes, and then went around his house sealing it up himself with silicone and expanding foam. And we did an air pressure test of that structure, and we found it to have a value of 7. Now, you have to have 3 or lower to be efficient, or feasible for MVHR. His was 7, so it wasn't actually efficient. There was another house where they had a professional builder. A bungalow came in, retrofitted and refurbished the house to be airtight, fitted the MVHR, and we tested that again afterwards, and its value was 5. So even it wasn't feasible enough. So you really, really have to know what you're doing to make an existing structure airtight enough to justify retrofitting an MVHR. The last building we looked at was actually a passive house building by an architect who was going to live in the house themselves, and its value was under 1. And indeed, the passive house standard is to get the air tightness of your structure below 1 to maximize the efficiency of these MVHR devices, in the fact that it's recovering more energy from the heat and supplying that into the return air, and you're not losing that valuable heat out through leakiness in your building. So that's why air tightness testing is very important when it comes to making sure these technologies work. Look there, the units: meter cubed of air for every meter square of surface area of the external per hour. That's what that unit means. Those of you who are used to the commercial setup, you're saying, well, if this is similar to this, then could we consider the industrial setup to be a passive house? Well, effectively, if I was to take the walkie-talkie in London and say we need to make this a passive house, I could probably keep a lot of the structure and keep a lot of the services even, but I'd have to completely rip off the facade. And put a proper facade on there that not only burns cars, but also has a lot of insulation, a lot of wall components, limited an amount of glazing, have high spec glazing, high levels of air tightness. And so the amount of heat, you see the tubes going in here, that's pumping in heat during the winter, and it's pumping in coolant during the summer, and it may even have to pump in both heating and cooling when it's doing full air conditioning, because to limit humidity, you have to cool right down to 12 degrees so that it drops all its moisture, and then warm back up again to comfort 18 degrees. And so that's why air conditioning, where humidity control is a point, is even more energy intensive, because you have to both cool and heat in order to condition that air. And so you would have to, instead of designing any facade you want, you'd have to limit that down so that the amount of energy being pumped in here is an absolute minimum, and most of the energy you get is from one of these 3 heat recovery processes. That's how you would make a big commercial building a passive house building. Key consideration is acoustics for noise. The early days of MVHR, they were quite noisy and quite a lot of complaints that this machine is just going all the time in my attic and I can hear it. The newer technologies are quieter. Also, just in big industrial facilities, if the architect is tight about how much space they give the air ducts, then those air ducts need to be smaller. And to perform, we may have to pump more air down through them. And the more faster air you have, the noisier you're going to get. If you want to quieten that air, it's actually the solution is often space. So like in a music venue, you're putting in the air conditioning as a big gentle giant because it's moving that air really slow, a lot of air, but quite slowly through the system in order to provide comfort to people sitting in an arena, because you don't want the noise to be interrupting the lecture theatre. So acoustics is a really important aspect of making this system work. And the last thing I'll say about MVHR, if you've watched the heat pump video as well, there is a very interesting piece of research that was published there in the November 2019 version of the SIBC journal, which compared all the options for high density residential living, so apartment blocks and things like that. And the kind of runaway solution was an MVHR, where you're taking heat out of your return air, but then having a second stage on here, whereby you have an inbuilt packaged unit. The whole thing is a packaged unit, a heat pump that is then pumping heat from your exhaust air into the fresh air as well. And remember, you can go right down to low temperatures and pump to high temperatures with a heat pump. You can't do that with MVHR. So a two-stage MVHR with exhaust air heat pump as a packaged unit was both constructability and performance the runaway winner in that analysis. It was a very interesting case study, and it may mean that lots of apartments and lots of high density living in cities, that will become the replacement type of system that we have for providing space heating in buildings. So that's a summary of MVHR. When we asked you, the participants, what you thought, most of you thought that it was a key technology, but maybe it has to work well with other technologies like heat pumps. Very few of you said it was a limited technology flawed to the UK. Some of you said it was key to every building. So the kind of passive house take, if you like, if everyone was doing passive house, you would just need MVHR. If you want to be a bit more generous on the levels of insulation, levels of air tightness, then you put MVHR and a heat pump together. So it's a good few people saying that as well, that the passive house only is the way to go. And there's a few comments there as well from participants. One on the long-term maintenance, especially of the structure. It might be airtight at the beginning, but you bring in someone to get cable TV or someone to drill the various times of the year you're drilling holes in the facade. You come back years later, does it still retain that air tightness? Sealants as well disappear. Silicon can erode after only 3 years if you've used silicon in your ceiling. Various things can erode and break up and become brittle over time. So, how often would you need to retest the ceiling levels of the building and maintain them and keep them up to date? The argument for mixed mode we talked about already, and the area of sound we talked about already. So some interesting concepts there. I think it will be a key technology, particularly in perhaps urban areas and areas where there's a high air issue outside, so there's either a noise or smog pollution issues outside. I think it'll be key, but I do still think perhaps natural ventilation will play a big role, especially in more rural locations, more exposed locations. So that's the summary of MVHR